All right. So in this case, we need to consider our exam revision of November. This is November 2024 exam on our question 3 for transformers. Actually, there were two question papers. There's question paper, there's another one, which is the replacement. So we are going to work with the replacement also and see how the questions were being given there. So quickly, guys, into our question. As you can see, this is just a revision here. Define the voltage regulation of a transformer. As we know, this is the rise or fall in secondary terminal voltage when the load is removed and applied voltage remains what constant or remains the same. So that is simply is the rise. All right, the rise or fall in secondary. So this is the secondary terminal voltage. All right, when the load, so take note there, when the load is what? Is removed. Is removed and the applied voltage there and the applied voltage remains the same and applied voltage remains the same or constant. So these are the condition, that is the condition actually for a voltage regulation. 3.2, there we are given information important for us to consider a 500 kVA single phase. All right, so let me just try and take my information. I'm gonna use this space, guys, for my information. So this is a 500 kVA single phase transformer. It has an iron loss of, take note, I told you guys, they will be trying to confuse you there, trying to figure out which type of loss is this one. So the iron loss, that is your open circuit. So they gave you the open circuit there, which is what? 2.9 kilowatt. That is the iron loss. Okay? They are trying to hide that from you guys. So the following data is also supplied, the voltages for the primary and the secondary, the winding resistance. These are the winding resistances, not equivalent, but winding resistance. To say for the primary, we've got V1, which is 6,600 volts, and we've got R1 for the winding, 450 milliohms. So milli, guys, that's times 10 to the exponent of -3. So that will give us what? 0.45. So that's 0.45 ohms. And for the secondary, we have got the same situation. The voltage on the secondary, which is 415 volts, and also its winding resistance, the milli there, times 10 to the exponent of -3. That was going to give us the resistance of the terminal of this, which is 0.0019. So this is what you're going to have. These are the winding resistances that we are given in this case. All right. So from this information, they are asking us to calculate each of the following for a load power factor of what? 0.8 lagging. So we are given the power factor of 0.8 lagging. For a power factor of what? 0.8 lagging. So this is it. So the questions 3.21, the full load efficiency. Full load efficiency. So guys, I talked about calculating of the efficiency on our introduction. You can calculate the efficiency at any load, if you still remember. Here we talked about this, and at full load, our K is supposed to be what? 1 at full load. So we're going to take our efficiency formula, apply all the information, So in this case, we'll see that, okay, let's write our formula, then see what is missing on our formula as we understand that the efficiency at any load can be given as Ks cos phi, which is our power factor, over Ks cos phi plus the open circuit plus K squared, the short circuit, times 100% like this. So we have the K because they said full load. So when you are given this condition for the full load, K is equal to what? K is equal to 1. Remember, guys, I talked about this. K must be equal to 1. The S is given. We already have that one. Power factor, we have it. The open circuit power, we have it. All right. But this one, we do not have. Short circuit. So as for the short circuit power, we do not have. And for the short circuit, guys, we are going to need calculations there. All right, let's see, because we do not have this one. So let's try to figure out from this information, what can we do to calculate the what? To calculate the short circuit power. Okay. Okay, guys, no problem. Let me bring you back here so that I can try to figure out how can I explain it to you. Remember, this is your short circuit test. And the short circuit power is this one. Can be given from I squared RE of the primary, this one, refer to the primary, or you can take it from the secondary side. So meaning to say we can calculate it from one of the sides, refer to the primary or refer to the what? To the secondary. So I'm going to take the one for the what? For the secondary side. Okay, so remember that our P short circuit is equal to I1 squared times RE of the second of the primary. Remember, I said I'm going to use the what? Primary side. Refer to the what? Referred to the primary. Referred to the what? To the primary. So you can use same information, but referred to the what? To the secondary, all right? So meaning to say, on this formula that we are having here, there is a need for us to calculate this. We're supposed to find I1. We do not have I1. We are not even given that. We need to find this RE1, and mostly RE1 maybe, it depends with the information. If we can have it direct. All right. So this is it. In previous cases, we saw that we were going to actually work with the ZE also. But in this case, guys, we are not going to work with that. We just need to find this RE. So where are we going to have it? Because this one, we can have it from what? From our apparent power there, the rating. S is equal to V1, I1. So we can find what? We can find I1 from there. This one, I1. We can determine it what? From S. Okay, let's start with that one first. Let's start with that one, guys. Let us just do it stage by stage. So to find I1 from what? From S. Okay, remember that S is equal to V1, I1. It can also be V2, I2, as we need the primary side. So it means I1 is equal to S over V. I also talked about these guys previously. So that's our S, 500 kilovolt amperes, 500 kilo times 10 to the exponent of 3. All right, V, this is V1, sorry. This is our V1, and we have got our V1, 6,600. So that was going to give us I1, guys, okay, which is 75. So that was going to be 75.758 amperes like this. All right, we have got a part that we need to use to calculate this short circuit. To calculate this short circuit. We have this I1 to calculate our short circuit. So as for the R there, the equivalent, this is the equivalent resistance. Guys, we used it to calculate it previously on the examples and other questions that I was using. from this short circuit power. But now we need to calculate that short circuit power. We do not have it. So what can we use now? We are limited because we do not even have the equivalent reactance or the equivalent impedance. They are not even there. We could have made that one the subject. Remember, from the method of referring, because we've got R1, we also have this R2, V1, and this V2. Remember, from the method of what? Referring. So we can calculate what? We can calculate this RE1. So from what? From the method of referring. From the method of what? Referring. We do understand that if we need the equivalent, if we need the equivalent resistance referred to the primary side, we are going to use R1 plus R2, this one. Okay, take note, this is R2 bar, which is represented by the formula R2 into the transformer ratio squared. This is the transformer ratio squared. In actual sense, it was supposed to be given as N1 over N2 squared. But in place of this N1 over N2, we do understand that V1 over V2 is equal to what? N1 over N2. So we are going to work with V1 and V2. So we are going to use V1 over V2 to the exponent of 2. That's our N5. This one is N5, guys. I'm not going to talk much. This is your N5 as it is this part. You see, guys, they want you to recall from N4. So please revise, guys, everything that you did in electrotechnics. All right. So our R1, guys, from the winding resistance there, we are given 0.45 ohms. Just going to substitute 0.45 plus R2. That was 0.0019. Okay. 19 into V1 over V2 squared. So V1, we have it. V2, we have it. 6,600. Our V1 over V2, which is 415 to the exponent of 2. That was going to give us the equivalent resistance in this case when we are referring to that, to the primary of 0.931 ohms. With this and the current of the primary, which is I1, we can calculate our short circuit power this way. So if we wanted, guys, we could have used what? Secondary side, referred to the secondary side, we work with that. It was going to be the same. So it is up to you. So that is it, guys. Let's calculate our short circuit. Remember our formula here, the one that I said we're going to use. So therefore, our short circuit power was going to be what? I1 squared RE1, which is I1. We have it 75.758. This is 58 squared times the equivalent resistance referred to the primary, which we calculated of 0.931. That was going to give us the short circuit power. Just like that. So it was going to be 5,343.265 in watts. You can even convert this to kilowatts, divide by 1,000. That will be 5,343. It's going to be 3 there. In what? In kilowatts. You can also write this in what? In kilowatts. Since we are also having the open circuit, remember we're given open circuit in what? In kilowatts. This was the missing part, the missing piece of the formula here. With this, efficiency can be determined, which is full load efficiency. You see, guys, they want you to figure out its mathematical presentations, substitutions, this and that. Formulas. Write down the formulas that are needed there. Figure out which one can I use. That is the case of your exam. So that is it, guys. Let's substitute our K. Remember, this is full load. Our K is 1. So that's 1 times S I'm gonna use it in kilovolt amperes as it is like that. So if I use this in kilo, I'm gonna use this in kilowatts. I'm gonna use this in kilowatts. That is what I'm gonna do. All right. So the power factor, cos remember they told us power factor 0.8 lagging. So that's 0.8 like that. All right. Everything over what? Gonna have the same presentation as it is in the numerator there. So that's 1 times 500 times 0.8. All right. Plus our open circuit. All right. We are given this one originally 2.9. We are given this. So that's 2.9. We are already given this. Remember, I used the kilovolt amperes. So I'm going to use what? Kilo also here. Kilowatt plus. Okay, sorry for that. That's plus K squared. Our K, remember, for full load, that's 1. So it's going to be 1 squared times that short circuit, the one that we have been calculating, guys, the missing piece of our question here. In kilowatts, since other values are in kilo. So I'm going to take in kilo. That was 5,343. This is the value that we have been calculating this one. Times 100%, we are done. So you have your efficiency, guys. Efficiency of the transformer can be calculated at any load, at any given load. So that was going to give us 97.981 percent, just like that. All right. So this is it, guys. Make sure you, okay, sorry for that. Make sure you go through your information, understand the way that you're given. So if you want to use this as 500,000, make sure that you convert this, you convert also this one. It is up to you. That one, it is up to you. So please do more questions. Like you can figure out past exam papers. Just try to figure out how do they ask these typical questions. So 3.22, the efficiency at half load. This time it is at half load. So what is just going to change is the K that we are going to have. So 3.22. Remember, they are saying at what? At half load. At half load, the K is equal to what? Half. That's 0.5. 50%. Remember, half load is 50%. So as a decimal, 0.5. So this is the only part that is going to affect our question. Everything, guys, is going to remain as it was before the values that we calculated. So this is 0.5 in place of K times our S, everything. Just going to repeat as it is times our cos. Remember, it was what? 0.8 lagging. All right. This one is just going to be a repetition. 0.5 times 500 times 0.8. Okay, plus everything, guys, your open circuit 2.9 kilowatts plus the short circuit, that one that we calculated. So it's K squared, which is what? 0.5 squared, K squared for our half load. Remember, K is what? 0.5. So that's 0.5 squared times our short circuit, guys, the one that we calculated, it was 5,343 kilowatts, just like that. So this is what you're going to have at what? At a half load. So if it was 3/4, 3 over 100, I mean 3 over 4, 3/4, write it as a decimal, is the same as 75%. You write as a decimal, 0.75. So you convert to a decimal, the K that you use. All right. Remember, I told you it's taken from 0 to what? 1. No load to what? To full load. In between, it must be a decimal in between. All right. So that is it, guys. Let us save our answer here. So that was going to give us 97,926. It's not even that much different from the first one. Okay, so that is what you're going to have. Just try to work out as many questions, guys, as you can. All right, let's see another question, which is 3.23 now. So this one, it was just a repetition of what? 3.21. Okay, I do not want to erase this formula. Maybe we might need it. Let's see. 3.23, the maximum efficiency. Calculate the maximum efficiency. So for us to have the maximum efficiency, first we have the condition for K for maximum efficiency, this one. We have the conditions for the K that we are going to use before we talk of that maximum efficiency. Remember, I said at maximum efficiency, K is equal to the square root of what? P open over P short circuit. With that K that you have calculated, you can substitute it back into this formula, this one. As long as you've got that K that you calculated, or you can substitute it into the special formula for maximum efficiency only. This one, it is used for maximum efficiency only. This one, it is used for at any, take note, guys. No, guys, you see, English is just not that deep, but if you take it another way, it will be something else. Here we are saying at any, meaning to say even at maximum efficiency, the formula can be used, guys. Bear it in mind. This one, it is just a special formula that we are saying when maximum efficiency occurs, our formula can be further adjusted to be like this. But what is important is okay. Yeah, okay, first. All right, so let's find our K, guys. Then you're going to use any method that you want. All right, so that's 3.23. The maximum efficiency is the one that we need. So we must find the K first at maximum efficiency. All right, why writing in words while I've already written here, guys? So at maximum efficiency, we do understand that K is equal to what? K is equal to the square root of P open over P short circuit. So what we just need is to substitute these as we have them. Open, it's already given in kilowatts, 2,9. The short circuit, remember, it is the one that we calculated. It is us who calculated this value. So we're going to substitute our value, guys. It was what? 5,343. We calculated this one. It is us who calculated. And this time we want a decimal, not a percentage. Is different from that person which said the percentage. There is just the K that we need, just right as a decimal. It was going to be 0.737 like this. So this is the K that we are going to use at what? At maximum efficiency. So using the formula, this one that I said at maximum efficiency, or using this one, we are going to have what? Same answers. All right. So that's it, guys. Use any part there. So I'm just going to use the one that is specifically meant for maximum efficiency. Not to say that the first one will be wrong. No, no, guys. No, guys. So let's use our formula. Let's substitute our values here. So our maximum efficiency from our formula, it is, I'm just going to substitute, guys. Remember, okay, let me just write it down. Ks cos phi like this. Ks cos phi plus 2 open circuit like that. All right, so we're going to multiply to 100%. So our K is the one that is at what? At maximum efficiency that we calculated this one. So we're going to substitute that 0.737 times S. I'm going to use it in kilovolt amperes, just like the previous case, 500. So that's 500 there. times, remember guys, your power factor does not change. It's still at 0.8. Okay, this part as a repetition, just repeat it as it is 0.7. 37 times 500 times 0.8. These ones, this one, the open is already given. Remember, they gave us originally, it's what? 2.9. So that one was an advantage. You're just going to use the original value that we have. So that's 2 times in kilowatts. Since here we are using kilovolt amperes. So let this one be what? Kilowatts. That's 2.9. Just like that. Just like that. Just like that, guys. You're going to obtain what? Your maximum efficiency. So with this information, substituting these values on your calculator, guys, it was going to be 98.071 percent. So this is our maximum what? Our maximum efficiency. So, or you can use the other formula that you are used to. All right. So I talked about these guys. So make sure that you go through your notes, question papers. It's going to be very, very important. Just like that. Then the last part, it is the output at maximum what? At maximum efficiency. What is the output there at maximum efficiency? So the output at maximum efficiency is given by KS cos phi in kilowatts, if you are using kilowatts. But remember already, guys, here we said at maximum efficiency, K is this. So we already calculated the K, guys. Just going to be substitute K 0.737. We already calculated that one. We are not going to recalculate whatever. No, 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 no. We already calculated this. All right. So that was our K. At what? At maximum efficiency. At maximum efficiency. All right. So times the S, our S 500 there. This is 500. It is in kilo. So our answer is going to be kilo also. Cos phi, which is our power factor of 0.8, that was going to give us 294.8. So this is what? Kilowatts. Kilo. The K is taken from what? From the kilovolt amperes. We used it in kilo. So our final answer also, let it carry what? Let it carry the kilo. This is output. You're talking about output power. Remember, we used cos phi power factor. Once the power factor is there, it means we are working our power in what? In watts, which in this case is going to be what? Kilowatts. So this is it, guys. Like I said, I'm going to bring you the November replacement again, the November 2024 replacement. Guys, I don't know what happened to have that replacement, but we are going to see in our revisions in our next class till we meet again.